shows up as an external force, and the reaction from the table will also appear as an external force, and the two of them will be in balance. There is no pressure when you choose the beaker containing water as your, to use a thermodynamic expression, as your system. But if you, so the next point is if the overall system is in equilibrium, every part of it is in equilibrium. So, similarly, if you apply F equal to ma for a larger system, you can keep applying it to smaller parts of it, which is the power of Newton's laws of motion. These in turn are applicable at the continuum scale. So, the natural laws at the continuum scale. So, if you work with a part of the liquid medium, then you have its weight appearing as an external force, and then you have pressure here, pressure here. So, these appear as additional external forces relative to this column of liquid, okay, which is how we were able to derive an equation of this type for pressure variation in a column of fluid. In general, we looked at many examples involving a liquid. So, if a rho depends on position, then you have to integrate this expression, and then hopefully you have knowledge of pressure at some location that will determine the constant of integration. So, this discussion on hydrostatics which is chapter 2 of the book, carries over when the object is in let us call it continuous motion in another direction. So, let us say we have this beaker containing water with a free surface, and let us say it is given an acceleration a x in this direction. Now, just for simplicity of analysis, we will assume that it is on rollers, so that friction is not really a relevant quantity. Then you could consider a column of liquid again. Now, you think of Newton's laws of motion as a vector equation, one the z direction, one in the x direction. Okay, so, in there is no motion in the z direction. So, the equation of hydrostatics remains unchanged, but in the x direction, how did we get this equation to start with? We had considered a small element and put pressure P here and pressure P plus delta P. At a distance, this is Z, this is Z plus delta Z, and this delta P was estimated as dP dz delta z, which is from your earlier courses, a small change. If I know the values of p at a location, I can estimate the value of p at a neighboring location if I know the gradients at the first point through something called the Taylor series expansion. Taylor series expansion holds for a point not only in the neighborhood, but anywhere. But if you pick the neighborhood to be small, then you can drop higher order terms, and then the first order Taylor series approximation is adequate to estimate pressure in the neighborhood of the point of interest. So, underlying this development is a mathematical structure called Taylor series. Which assumes that the function p is differentiable. So, with the same logic, now you can apply pressures on the left face and the right face of the fluid element and derive rho ax is the x component of the acceleration. Now, it is very clear that p is now a function of both x and z, and therefore, these derivatives have to be written as partial derivatives. The second equation is minus partial derivative of p with z is equal to rho g. So, we have you may think of it as a beaker carrying water. More generally, it is a tank carrying a liquid with a free surface, and it is moving at constant acceleration. If acceleration is 0, it is the equation of hydrostatics. Nothing happens. P is not a function of x in that case. So, this A x is taken to be spatially uniform. So, in this integration A x is constant, it does not depend on x or z. Every point has the same acceleration, that is equivalent to calling it rigid body motion of the body of liquid. So, equations of hydrostatics get extended to liquids undergoing rigid body motion. So, I am sure you can integrate these equations. Each person will have his own style. The method given in the book, you start with the second equation and write p, which is a function of x and z, is equal to minus rho g z plus the constant of integration can now be a function of x. So, put this equation in the first part and get, so the derivative of rho g z with x is 0. So, you get minus f prime x is equal to rho a x. So, f x is equal to minus rho a x times x plus some constant. This is now a strict constant which does not depend on either x or z. So, p x z is equal to minus rho g, I am sorry, minus rho g z plus a x x plus constant. So, g times z plus a x times x plus constant. This is the pressure variation. So, on the free surface, P is equal to P atmospheric, then the Z will have some shape, let us call it G x. Okay, so, substituting you will have P atmosphere I think this G, just want to avoid repetition of symbols. So, let us call this Z tilde. So, this is the equation for the free surface Z tilde, and how does it vary with x? Rest of it is constant, P atmosphere is constant, this constant of integration is a constant. So, you can see that Z tilde will have a negative coefficient, A x is positive. So, the coefficient of x is negative. So, the free surface develops, it is linear because it is proportional to x, and it has a negative slope. Like that. So, if you have a tank containing liquid moving to the right, then the free surface will develop a slope which is negative, okay, relative to the acceleration. Okay, so, the free surface can deform when the object is given some acceleration. A simple extension of this problem is when you have rigid body rotation. So, this rotation can be a very complex quantity, but very involved, but let us take a simple configuration. So, this is a vertical tube. So, we will call it rigid body rotation. So, the coordinates are r and z, and r coincides with the or starts with the axis of rotation. Omega is constant, there is no angular acceleration, but even a constant omega can give rise to acceleration of the fluid because it is moving on a curvilinear path. What is moving on a curvilinear path? The fluid particles, so to say. In our analysis, that would be a small element that is taken up for analysis. That acceleration will be centripetal and will be like A x, here it will be directed inwards. So, it will be v minus v square over r. So, like we have two equations in x and z, we have two equations in r and z. Where v is equal to omega r. Okay, so, once again you can integrate these equations. Equal to minus rho g z plus some function of r, and then putting them in the second equation, minus f prime r is equal to minus rho omega square r. In problems involving motion, it is not that immediately everything is set up, there is a build up time. So, this result holds after rigid body motion or rigid body rotation has been established in the system being studied. Okay. Here it is a body of liquid contained in a tube. So, integrating F r is equal to rho omega square r square over 2 plus this is constant. Let me just actually there is when you get f prime r, yeah, so this is all right. So, now substituting and using the same logic that on the free surface, this is the free surface, P is equal to P atmospheric so P atmospheric is equal to minus rho g z plus rho omega square r square over 2. So, this is z tilde plus constant. So, z tilde scales with omega square r square. So, with a positive sign, so that is a parabola. So, as you rotate the tube about its axis, it will develop a shape like that. And that dip in the center will change with omega. See, many of these problems, particularly those given in the book, these have fairly important applications. For example, we saw force acting on the wall of a dam. I think you can imagine the importance of that subject. Force acting on an immersed body. It's a very important subject by itself. All of them have tremendous application potential. This is one reason why this Frank White book is so popular, because they are all simpler versions of very important subjects. So, you can think of milk being carried in a vessel, in a huge tank, giving rise to surface deformation. So, here this I think it is there in the book. It says this liquid is mercury and it is kept in a tube with a very large diameter, and you rotate, it generates curvature, which can then be used as a mirror, liquid mercury being a good reflector. And what is the advantage of that arrangement? Why use a liquid mirror? Because its focal length can be altered with omega. It's a very important benefit you get. So, these little problems given in the book have interesting, important applications. So, when you have rigid body motion, you can extend hydrostatics, okay, because in one direction you continue to have pressure gradient proportional to depth from the free surface. So, I would like to work out some examples, some more examples from the book. So, these are forces acting on immersed objects. I have sent you the tutorial problems also. So, in the tutorial you will continue discussing hydrostatics. Subsequently, in fact, in our class on Wednesday, our fluid will start to move. Okay, not in a trivial manner. The rigid body motion you can think of as trivial, same velocity everywhere. It will move in a non-trivial manner. And then what are the applicable equations, what are the applicable natural laws? We are in the continuum domain. Natural laws will be the laws of continuum mechanics, essentially in a Newtonian framework. Okay. So, it's F equal to ma, that is the domain. That is the baseline. So, this problem you have seen, but I thought I would repeat. So, there is a wall on the right hand side. So, on the wall you have pressure variation like this. So, let us say this is the z coordinate. Now, you know that calculations depend on how the coordinate system is chosen. I want to emphasize here that in your exam, whether it is a quiz or a mid-semester exam or the final, the burden of convincing the grader that you know the subject, the burden is on you. It is not a big burden, all you have to do is show the coordinate system. Now, my hand is not very stable on this, so my vertical line is not really vertical, but that does not mean you have the freedom to draw shabbily. Please use a scale. Okay. In the exam, draw your figures neatly, show the coordinate system. As we go along, you will encounter the familiar, I may call them beasts called free body diagrams. So, those have to be carefully shown. Only then can you sum all forces equal to mass times acceleration. Those forces have to be vectorially added. So, the best is you show components and add component wise. What components to use depends on the choice of your coordinate system. So, this is the pressure distribution acting on the vertical wall, which is rho g h minus z, okay, plus atmospheric. So, either you show atmospheric pressure explicitly or you just work with the gauge pressure. Okay. You can see that if z is equal to 0, it is rho g h. If z is equal to h, it is 0. Okay. So, the resultant of this force F is obtained by integrating pressure, which will turn out to be just rho g h h over 2. Okay, so, this is how you find the force acting on the surface. That is, you consider a small element d z, and the force acting on the small element is p z d z, integrate over the entire surface. And the next is the point of action of this force. Let us call this h x, because it is the position of the x component of the force. That is obtained as and when you substitute all these quantities, you will get h x equal to h over 3. Okay. So, for this simple problem, which you will keep encountering. So, if you wish, you can use this result that on a vertical surface, it is maximum pressure, which is at the base, multiplied by the height divided by 2 will give you the resultant force, and its point of action is 1/3 h. So, I am doing this because last time some students came running and said, what is this p x dx or p z dz? So, I thought I would just repeat. Now, let us look at a slightly more difficult problem, where the shape of the object is not either vertical or planar. It is a parabola. So, we have ground and we have water. So, the shape of the parabola z is again z. Its origin is over there, and the shape of this parabola is z over z 0 x over x 0 whole square, where z 0 is 7 meters, x 0 is 3 meters. This is x 0 and this is z 0. So, find the forces acting on this surface, which is the shape of a parabola. So, what is the pressure distribution in case you want to visualize it? This is the parabola. So, at the top it is 0 and it will act normal to the surface. So, let us show it like this, and at the base it will be much higher, because pressure increases in the direction of the depth, like this. Okay. So, this is the pressure variation. Okay, you may distinguish, it's a good point. So, you may distinguish between fully immersed objects and objects on which you have a liquid column on one side. Okay. In both cases they are immersed. In one case you will have a, let us say, a ball immersed in water, that is fully immersed. Okay. Here it is partially immersed, but both are immersed. Okay, so I think in the previous example we had a part of a circle and we parametrized it with r sin theta and r cos theta, etc. No, not slanting. The surface is, this is the surface being evaluated. It is immersed in a fluid medium, because you have water on the left hand side and air on the right hand side. You have atmospheric pressure uniformly from the right, which cancels off with the atmospheric pressure at the top. Okay. So, that is, we set them both to be 0. Okay, so one approach, the long hand approach, is to parameterize this parabola in terms of some angle, okay, like we did for a circular boundary. That is one approach, or we can use the result obtained last time. So, this is a very powerful application of that result. What was that result? That the vertical force will just be the weight of the liquid column above, and atmospheric pressure again cancels off, assuming it is atmospheric on the right as well as above the free surface, atmospheric pressure being constant over the domain being analyzed. Okay. So, set atmospheric pressure 0, then the vertical force is the weight of the liquid body above the object, above this surface, above surface. So, we may call it A B. So, you can draw a line like this, and then the weight of this liquid body will act as, this is F vertical. How much is that weight? Okay, now we are working with two dimensional objects, that means the object is unchanging in the other direction. So, per unit meter normal to the plane of the blackboard, the weight will be area times density. Okay. So, F b will be area times density times g. Okay. And how much is this area? Well, you may remember some formula, otherwise you can quickly integrate. Integrate, what is it? You take a strip x dz, integral over 0 to z 0, correct? Or you can take a vertical strip and say z dx going from x equal to 0 to x 0. So, I am sure you can find the area. So, this element is x dz. So, f v is equal to rho g integral z equal to 0 to z 0 x dz. So, substitute for x from the function this z over z 0 equal to x over x 0 square. From there you substitute for x and then you can evaluate this integral. This will be in units of Newton per meter. Now, what will be the point of action? What is the point through which this vertical force will act? It will be the center of gravity of that liquid body, but because density is constant, it is also the centroid. Okay, so, so, this distance, I think let us call it x c g. C g of this centroid turns out to be 3/8 x 0. So, standard result I picked up from some mathematics handbooks. Okay. So, this is a shortcut calculation for finding F v without having to integrate the pressure distribution. Okay. Now, you can do the same thing for F horizontal. What do you do for F horizontal? You project the parabola onto a vertical line. Okay. So, which is the same as the problem we had last time. Okay. So, that F horizontal will be rho g z 0 divided by 2 multiplied by z 0, right. Instead of h you will have z 0 and the point of action will be z 0 divided by 3. Okay. So, that will give you f h. So, for that you project the gate that has the shape of a parabola onto a vertical line, and then on that line it's you have pressure variation from the base to the top. It's a linear variation. It's the same analysis as last time. So, F h will be equal to rho g z 0 divided by 2 and the point of action is z 0 divided by 3. So, this point of action is important because this is the external loading. Suppose you carry out, we have analyzed from the fluid side. Now, for let us say all round analysis, you also have to analyze from the side of, from the viewpoint of the gate. So, let us say you find out that reactions at the base at point A are very large, then this gate will start eating into the soil and keeps deforming, keep moving. Okay. So, you have to find out what are the reactions, let us say at a point like A. Gate also has to be supported, let us say at point B. Now, if you use a nut and bolt arrangement, let us say, so how big should the bolt be? Okay. If the forces are very large and you put a small nut and bolt combination, it is going to break. So, you have to analyze the gate from its structural integrity perspective, for which you will need external loading, which comes from this F v and F h. So, the first cut analysis can be carried out with F v and F h, but if you have let us say you already have a lot of experience and insight, you could work with the pressure distribution. So, first cut analysis with F v and F h, detailed analysis with the pressure distribution. So, why pressure distribution? Well, let us say the ground moves, then you are no longer in the domain of hydrostatics. Okay. Then you have to bring in fluid motion into consideration. Then these pressures will depend on not only the vertical coordinate, but also time. Accordingly, F v and F h will change with time, and their point of application will also change with time. Then it is no longer very useful to have effective forces for your description. You are better off staying with pressures. So, you can see that fluid motion suddenly takes you into a somewhat complicated domain, which is why it is going to take us more time understanding it, starting Wednesday. Okay, so, let us look at, just to where is it? Yeah, this is an example. So, recall that pressure varies with altitude in the atmosphere. Now, we are talking about the atmosphere. How does it vary? Does it increase or decrease? Decreases, and if you make some approximations like constant temperature, it is an exponential variation, exponentially decreases. Now, like that, how much is the value of P at z equal to 0? Atmospheric pressure. Okay. How much is atmospheric pressure? Roughly some 1.01 bar or something, right? 1.0135 or something bar. 1 bar is 10 raised to 5 Newton per meter square. So, in this problem, so you start with a balloon. This is a small balloon that is kept at the ground level. This is small compared to the atmosphere. The balloon is not small per se. So, the balloon in that problem given in the book has a diameter of 2.5 meters and is filled with helium, and the helium plus balloon material combo has a weight of some 6, rather a mass. So, at z equal to 0, let us say rho is equal to 1.2 kg per meter cube. Now, if it is an exponential variation for pressure, exponentially decreasing pressure, and let us say temperature is sensibly constant, slightly decreases, but more or less constant, what will be the variation of density? It will be like pressure, right, for air. So, it is almost an ideal gas. So, density also will decrease exponentially. So, please revisit that problem where we did hydrostatics of the atmosphere. So, now the first question is, will this balloon tend to rise? So, you have to realize that this balloon, when it is kept in air, will experience buoyancy. How much is buoyancy? Buoyancy will be volume of the balloon times rho of air outside. Okay. If that exceeds 6.7, then you know buoyancy is greater than weight, and then the balloon will tend to rise. Okay. So, the problem is stated in such a way that indeed it is going to rise. Okay. So, first is show that balloon will rise. So, balloon volume is equal to some 4/3 pi r cube meter cube. So, if rho air times this volume exceeds 6.7, then balloon will rise. Due to buoyancy. Okay, so, in this problem it turns out it is going to rise. The next part of the problem is, see, balloons are of course, they are used, this is a 2.5 meter cube balloon, 2.5 meter diameter balloon. It is not meant for just entertainment, it is used for measurements. Okay. So, measurements of pressure, temperature, humidity in the atmosphere. The second part of the question is, find out where it is going to stabilize, how high will it go. So, it will go to a point where air density drops. So, that local air density times balloon volume is equal to 6.7. At that point it will stop. Okay. So, that turns out to be some, how high do you think this balloon will rise? How high do they usually rise? It's a few kilometers, some 2, 3, maybe 3, 4 kilometers, quite a bit. So, a very simple arrangement like a balloon can go up to 4 kilometers. Okay. Can you go with it? Yes, provided the same criteria, the equations of hydrostatics and buoyancy have to be satisfied. Okay. So, I think many of you have a class. So, we continue on Wednesday.